Our galaxy is racing through space at over 1,000,000 miles per hour. This journey will reveal the true, invisible force behind that astonishing speed. For decades, scientists believed a hidden concentration of mass, dubbed the Great Attractor, was pulling us through the cosmos, but the numbers never quite added up. The full force driving our motion remained a cosmic mystery. Today, we are going to solve it. You will understand how the largest structures in the universe dictate our fate, and you will discover that our ultimate destiny is shaped not just by what is out there, but by what is not. We are being pushed by an abyss. What does the emptiness of the universe make you wonder about most? The truth is, our cosmic journey has always been a story of two forces. For a long time, we only knew half of it. Our galaxy is not just moving, it is being pulled. And for decades, the prime suspect in this cosmic tug of war had a name, the Great Attractor. This name itself was a placeholder for a mystery, a dense, hidden region of space in the direction of the constellation Centaurus that seemed to be exerting a colossal gravitational pull on our entire galactic neighborhood. The problem was, we could not see it directly. Our view to that part of the cosmos is completely blocked by the thick, dusty plain of our own Milky Way. It is like trying to spot a distant mountain range through a dense, perpetual fog bank. Astronomers could only infer its existence by watching how thousands of galaxies, including our own, were streaming toward this one invisible point. The motion was undeniable, a vast river of galaxies all flowing in the same direction. So, the Great Attractor became the accepted explanation, the massive hidden anchor around which our local universe seemed to revolve. But as measurements became more precise, a nagging question arose. Was the pull of the Great Attractor truly strong enough to account for the breathtaking speed of our entire galactic journey? The math hinted that something was missing, that the full story of our motion was still incomplete. The numbers told a story the Great Attractor could not finish. When astronomers finally pieced together the math, they realized its gravitational pull was simply not powerful enough. It was like trying to explain why a sailboat is racing across the water by pointing only to a gentle breeze. The breeze is real, it is helping, but it cannot possibly account for the boat's full, surging speed. There had to be a hidden current beneath the surface, a second, even more powerful force at work. Our galaxy's immense velocity, over 600 kilometers every single second, demanded a bigger explanation. This was the heart of the cosmic mystery. For our motion to make any sense, the equation of the universe needed a second term. The Great Attractor was pulling, yes, but something colossal had to be pushing. The search was no longer just for a hidden mass, but for a hidden force, and the clues would lead to a place where nothing seemed to exist at all. The breakthrough came not from looking at what was there, but from mapping what was not. In 2017, a team of astronomers led by Yehuda Hoffman at the Hebrew University of Jerusalem published a study that turned the cosmic mystery on its head. They proposed a radical new force shaping our journey. It was not a second, more powerful attractor. It was something fundamentally different, a repeller. The idea is rooted in the very nature of gravity itself. We think of gravity as a pulling force, which it is, but that pull is relative. Imagine you are standing in a room that is perfectly, uniformly crowded. The gravitational pull from every direction cancels out, and you feel no net force. Now, imagine one wall of that room suddenly vanishes, leaving a vast, empty space behind it. You would not be pulled from the front, you would be pushed from behind. The greater density of the crowd at your back would exert a net force, shoving you toward the emptiness. This is the essence of the dipole-repeller. It is not an object, it is a colossal void, a region of space spanning hundreds of millions of light years that is astonishingly empty, containing far fewer galaxies and far less matter than the cosmic average. This immense underdensity, this gaping hole in the cosmic fabric, creates a gravitational push. Because the universe around it is denser, that surrounding matter exerts a greater pull from the opposite direction, effectively propelling our galaxy away from the void. The dipole repeller sits in the cosmic sky almost exactly opposite the Great Attractor. So, as we are pulled toward the hidden mass in one direction, we are simultaneously pushed from behind by the profound emptiness in the other. Our motion is the result of this cosmic imbalance, a grand tug of war between a hidden mountain and a hidden ocean trench. This idea forces us to rethink gravity itself. We are taught that massive objects pull on one another, and that is true. But the deeper truth revealed by Einstein is that gravity is not a force in the traditional sense. It is the geometry of the universe. Mass and energy curve the fabric of space-time like a heavy ball placed on a stretched rubber sheet. Objects then follow the curves and dips in that fabric. Now picture that rubber sheet not with a single heavy ball, but with an entire landscape. Some areas are hilly and dense with matter, creating deep gravitational wells. Other areas are flat, empty plains. This is the key to understanding the push of nothing. The dipole repeller is one of those vast, flat plains. It is a region of space-time that is far less curved than the cosmic average because it contains so little matter. Our local group of galaxies, by comparison, sits in a slightly denser, hillier neighborhood. And in this cosmic landscape, motion is not about being grabbed. It is about rolling downhill. From our position in the denser region, the slope of space-time tilts away from the underdense void. We are, in effect, rolling down into the valley that surrounds the Great Attractor, pushed from behind by the relative flatness of the repeller. So the void does not exert an active, repulsive force. Instead, it creates a gravitational slope by its absence. The greater density everywhere else does the work, nudging us toward the nearest deep valley and away from the flat, empty plateau. Our entire galactic journey is a slow, inevitable roll along the contours of an invisible landscape shaped by both mountains and absences. This cosmic landscape of hills and plains is not random. It forms a pattern on the largest scales imaginable, a grand architecture known as the cosmic web. To truly grasp the dipole repeller, we must first understand this web and our place within it. The universe is not a uniform soup of galaxies. Instead, it is structured like a colossal sponge or a vast neural network stretching across billions of light years. This web is made of three primary components. First, the dense knots, where thousands of galaxies swarm together in massive clusters. These are the mountain peaks of our cosmic landscape. Second, the filaments, long, thread-like bridges of galaxies and dark matter that connect the clusters. These are the mountain ridges. And third, the voids, the immense, bubble-like empty spaces that make up most of the volume of the universe. These are the vast, flat plains and deep valleys between the ridges. Our own Milky Way galaxy resides within a filament, a relatively dense strand of the web. The Great Attractor is a particularly dense knot where several filaments converge, and the dipole repeller, it is one of those titanic voids. It is not a perfect, absolute vacuum, but a region of extraordinary emptiness, a bubble in the cosmic foam that is hundreds of millions of light years across and contains only a sparse sprinkling of isolated galaxies. Visual simulations of this web are breathtaking. They show a luminous, intricate network of light set against an overwhelming darkness, a delicate lace of matter stretched across a void of incomprehensible scale. We are but a single, tiny point of light on one of those glowing strands, caught between the gravitational pull of a dense knot ahead and the effective push of a vast, empty bubble behind. Our entire motion is simply us following the flow along the filament, rolling from a place of relative density toward an even greater density and away from a profound emptiness. This is the true context of our journey. We are not being aimlessly pulled through a featureless darkness. We are navigating the largest structure in existence, flowing along currents set in motion by the very shape of space-time itself. This vast, empty plane has a location on the cosmic map. The dipole-repeller lies in the direction of the constellation Columba, the Dove, almost perfectly opposite in the sky from the hidden Great Attractor. If you could see the invisible architecture of the universe, you would find one of its greatest voids sitting there, a spherical region of profound emptiness. Its scale is nearly impossible to comprehend. This void spans roughly 300 million light-years across. To grasp that distance, consider that a single light-year is about 6 trillion miles. This void is 300 million times that length in every direction. It is so large that our entire local group of galaxies, which includes the Milky Way and Andromeda and spans about 10 million light-years, would be a mere speck within it. This single void is larger than the biggest known superclusters of galaxies. It dwarfs the famous Sloan Great Wall, one of the largest structures we have ever identified. We are talking about a hole in the universe so immense it could swallow thousands of galaxy clusters without a trace, and it is mostly empty space. This sheer scale is precisely why it is so difficult to observe directly. How do you see nothing? Astronomers cannot point a telescope at a void and take a picture of darkness because the darkness is everywhere. Instead, they must map it by its absence. They painstakingly chart the positions and motions of millions of galaxies across the sky, building a three-dimensional census of the cosmos, where they find a gigantic spherical region with a startlingly low number of galaxies, a place where the cosmic web has a gaping hole. They have found a void. The dipole-repeller was not seen, it was inferred, a ghostly silhouette revealed by the glowing structures that surround it. We know it is there because everything around it is moving away from it, and we are part of that universal flow. So the next time you look up at the night sky, remember that our motion is guided not just by the stars you see, but by an unimaginable emptiness in the constellation of the Dove, a void so large it helps push the Milky Way on its eternal journey. Mapping an absence is one of the greatest challenges in astronomy. We are fundamentally observers of light, trained to find and study points of illumination in the darkness. A void, however, is defined by the lack of those points. How do you chart the shape of a hole when you can only see the material around its edges? You cannot simply point a telescope at the dipole-repeller and take a photograph because your image would show little more than the blank space between foreground stars. The void itself is invisible. To uncover it, astronomers had to become cosmic detectives, piecing together its silhouette from indirect clues. The primary method involves creating incredibly detailed three-dimensional maps of the universe. This is done through massive redshift surveys, projects that catalog the positions and distances of millions of galaxies. Redshift is the key, the telltale stretching of light from distant galaxies that tells us how fast they are moving away from us and, by extension, how far away they are. By plotting the locations of all these galaxies, a map emerges, and on that map, the dipole-repeller appears as a staggering spherical gap, a bubble hundreds of millions of light-years wide where the pinpoints of galaxies simply vanish. The map shows a dense, luminous cosmic web everywhere else, and then this vast, dark sphere of near-nothingness, but the map alone is not enough. To confirm this void is actively influencing motion, scientists looked at the galaxies that do exist near its borders. They studied their peculiar velocities, which are the slight deviations in a galaxy's motion caused by local gravitational tugs, separate from the overall expansion of the universe. They found a consistent pattern. Galaxies on the side of the void facing us were showing subtle motions away from the emptiness, as if being pushed by the greater density behind them. It is like deducing the presence and strength of a wind by watching how leaves on the edge of a calm courtyard are all rustling in the same direction. The leaves are not in the wind itself, but their motion reveals the invisible force. By combining the stark evidence of the map, the giant empty bubble, with the kinematic evidence of the galaxy's motions at its edge, the case for the dipole-repeller became undeniable. We discovered a dominant force in our cosmic journey, not by looking at it, but by reading the subtle reactions of everything surrounding it. The evidence was written in the motion of the galaxies themselves. To prove the existence of a void pushing us, the team led by Yehuda Hoffman needed to move beyond a static map of where galaxies are. They needed a dynamic map of how they are moving. This required an extraordinary dataset, one that catalogued not just positions but velocities. Their key resource was a project called Cosmic Flows 3, a monumental compilation of the precise distances and speeds for over 8,000 galaxies in our local universe. Think of it as a cosmic traffic report, but instead of cars on a highway, it tracked entire galaxies drifting through the expanding fabric of space. Hoffman's team fed this immense catalog into supercomputers, which then performed a reverse engineering calculation on a cosmic scale. They asked one fundamental question: given the distribution of all the mass we can see and infer, what gravitational landscape would produce the exact motions we observe? The computer model began with the known attractors, like the Great Attractor and the even more massive Shapley supercluster far beyond it. It calculated their expected pull. Yet when the simulated motions were compared to the real, observed flows from Cosmic Flows 3, a glaring discrepancy remained. Our galactic neighborhood was moving faster than those attractors alone could explain. Something was missing from the equation. The model needed an additional component to make the math match reality, and that component was not another pull but a push. When the researchers added the gravitational influence of a vast underdensity, a profound void in the direction of Columba, the simulated galaxy motion suddenly snapped into perfect alignment with the observed data. The coherent flow they discovered was unmistakable. Thousands of galaxies, including our own, were showing a systematic drift away from that specific region of space. It was as if every leaf in a forest was rustling, not because of a wind blowing toward them, but because of a silent pressure from behind. This was the smoking gun. The galaxies were not being sucked toward the void, they were being repelled by it, or more accurately, pushed from the denser regions adjacent to it. The pattern in the data was a clear signature of avoidance, a grand exodus away from emptiness. This analysis transformed the dipole-repeller from a speculative idea into a quantifiable feature of our cosmos. It proved that our motion is not a simple attraction to a single point, but a complex response to the entire gravitational landscape, where immense nothingness shapes the flow of everything. This cosmic traffic report was only possible because of a revolution in computing power. To turn those thousands of galaxy velocities into a map of invisible forces, scientists had to build a digital universe inside a supercomputer. They start with our best understanding of the laws of physics and the initial conditions of the Big Bang. Then they let the simulation run, watching as gravity sculpts a virtual cosmos over billions of years of digital time. Dark matter forms an invisible scaffold, and ordinary gas and galaxies fall into its gravitational wells, gradually weaving the cosmic web of filaments, clusters, and voids. These are not simple animations, they are vast numerical experiments that test our fundamental theories of how structure forms. For years, simulations that included only the known massive attractors consistently produced a problem. The predicted flow of galaxies in our local region was too slow. The simulated Milky Way simply did not move with the breathtaking speed we observe in reality. It was a persistent, glaring mismatch between the model and the universe. The equations were correct, the physics was sound, but a key ingredient was missing from the recipe. The breakthrough came when researchers introduced a new variable into the digital cosmos, not more mass, but less. They carefully inserted a vast, spherical region of profound underdensity into the starting conditions of the simulation, positioned opposite the Great Attractor. Then they set the universe in motion again. As the digital eons passed, the void evolved, growing emptier as matter flowed out toward the denser regions around it. And when the simulation reached the present day, the result was unmistakable. The predicted velocity of the virtual local group of galaxies now matched the real, observed speed with stunning accuracy. The model had finally reproduced reality. This was the definitive validation, the digital proof that the void was not a coincidental absence, but an active, dynamic player in the cosmic tug-of-war. The supercomputer had revealed that our motion is the precise outcome of a balanced equation, a perfect tension between the deep gravitational well of the Great Attractor ahead and the expansive, flattening slope of the dipole-repeller behind. We are caught in the middle of a push and pull that has been shaping our path for billions of years. This understanding forces a new question about the emptiness around us. The universe is filled with voids, vast bubbles of nothingness that make up its largest structures. So what makes the dipole-repeller so special? Why does this particular void have such a profound influence on our galactic journey, while others seem like passive background scenery? The answer lies in a combination of scale, location, and a unique partnership. Consider the famous Boötes void discovered in the 1980s. It is often called the Great Nothing, a spherical region about 330 million light-years across that contains only a handful of galaxies. In terms of sheer, staggering emptiness, the Boötes void is a champion. It is one of the largest known voids in the universe, but it does not dictate our motion. Why? Because it is not aligned with our flow. The Boötes void is located in a different part of the cosmic web, its gravitational slope tilting in other directions, influencing other galaxies in other filaments. It is a magnificent desert, but it is not the desert behind us. Closer to home, we have the local void, a smaller but significant empty region right on our galactic doorstep. This void, pressing against our own local group, does give us a slight nudge, contributing to our motion. But its push is minor compared to the colossal shove from the dipole-repeller. So the dipole-repeller's first unique feature is its specific perfect alignment. It sits almost exactly opposite the Great Attractor in the sky, creating a clear dipole axis, a line between a point of immense density and a point of profound emptiness. We are on that line. This precise alignment amplifies its effect, making it the dominant push in the cosmic tug-of-war governing our local universe. It is not necessarily the largest void, though it is among the giants. Its power comes from its position. It is the void that happens to be in the driver's seat for our particular filament of the cosmic web. Furthermore, the dipole-repeller is not acting alone. Its influence is measured and confirmed specifically in opposition to the Great Attractor. They form a pair, a gravitational dipole. One is not meaningful without the other in explaining our motion. Other voids, like the one in Boötes, are incredible and mysterious in their own right, but they are solo acts. The dipole-repeller is part of a cosmic duet, and we are the audience moving in rhythm with its balanced, opposing forces. This partnership between a hidden mountain and a hidden ocean trench is what truly sets it apart, making it the key to solving the decades-old mystery of our million-mile-per-hour journey through the dark. But if a local void can push our galaxy, could it also be subtly warping our view of the entire cosmos? This question brings us to the edge of one of the biggest mysteries in modern cosmology, the Hubble tension. At its heart, this is a disagreement about a single, fundamental number, the Hubble constant. This number tells us how fast the universe is expanding at the present moment. For decades, astronomers have tried to pin down its exact value with ever greater precision. Yet two of the most trusted methods now give stubbornly different answers. One method looks at the early universe, at the faint afterglow of the Big Bang known as the cosmic microwave background. The other method measures distances and speeds of nearby celestial objects like supernova and variable stars. These are our local cosmic yardsticks. The problem is, the local measurements consistently suggest the universe is expanding a bit faster than the pristine early universe data predicts. The numbers disagree by just a few percent, but in a field built on exquisite precision, that gap is a chasm. It suggests a fundamental flaw in our understanding, a potential crack in the standard model of cosmology. This is the Hubble tension, and it has physicists considering everything from new particles to altered gravity. But there is another, more subtle possibility, one where our discovery of the dipole-repeller plays a crucial role. Could local motions like our own million-mile-per-hour flow away from the void, be introducing a tiny bias into those local measurements of the expansion rate? The answer is a cautious maybe, and it is an active frontier of research. The logic is straightforward. To measure the Hubble constant locally, astronomers observe objects like a certain type of supernova, a stellar explosion that acts as a standard candle. They measure how bright it appears from Earth to gauge its distance. Then they measure the object's redshift, how much its light is stretched, to see how fast it is moving away from us. The relationship between its distance and its recession speed gives us the expansion rate, but here is the catch: that redshift measurement includes everything. It includes the smooth, uniform expansion of the universe, which is what we want to measure. But it also includes the object's own peculiar velocity, any local motion caused by the gravitational tug of nearby galaxies or clusters. And crucially, it includes our own peculiar velocity as well, the motion of the Milky Way being pushed by the dipole-repeller and pulled by the Great Attractor. If we are moving toward or away from a distant supernova because of these local flows, its light will be slightly more redshifted or blueshifted as a result. It is like trying to measure the speed of a river's current while you yourself are drifting in a boat. If you do not perfectly account for your own drift, your measurement of the current will be off. For decades, astronomers have tried to correct for these local motions using models of the gravitational landscape. But if our map of that landscape was incomplete, if we were missing a major component like the dipole-repeller, then our corrections were also incomplete. Our own unaccounted-for motion could have been subtly contaminating the data, making the local expansion rate appear slightly different than it truly is. Recent studies suggest this local flow effect might account for a small part of the tension, perhaps a third of the discrepancy. It is not enough to solve the entire puzzle, but it is a vital piece of the calibration. It reminds us that we are not passive, fixed observers of the cosmos. We are participants caught in a dynamic flow, and to see the universe clearly, we must first understand our own place within its grand and shifting currents. Our path through the cosmos is a grand arcing curve, a trajectory set billions of years ago. The Milky Way, along with our entire local group of galaxies, is not drifting aimlessly. We are on a specific course, a river of stars flowing along a filament of the cosmic web, guided by the immense gravitational landscape shaped by the two giants in our story. Ahead, the hidden mass of the Great Attractor pulls us inward. Behind, the profound emptiness of the dipole-repeller gives us a steady, relentless push. This combination of pull and push does not send us in a straight line, but along a curved path, as we are also influenced by the gravitational tugs of other nearby clusters and filaments. Think of it as a leaf caught in a complex current, where the main flow is set by the largest forces, but smaller eddies and swirls nudge it along a specific meandering route. Our ultimate destination is the heart of a gathering, a future collision course with our largest neighbor, the Virgo cluster, and beyond that, the even more massive Laniakea supercluster, of which the Great Attractor is a central hub. We are, in essence, flowing downhill into the deepest gravitational well in our local universe. The timescales involved are almost beyond human comprehension. This journey is measured not in years or centuries, but in cosmic epochs. It will take our galaxy and its companions billions of years to complete this migration. The merger with the Andromeda Galaxy, a monumental event for our local group, will happen in about 4 billion years, a mere side note on this longer voyage. The full journey toward the heart of Laniakea will unfold over tens of billions of years, a slow-motion procession that began when the universe was young and will continue long after our sun has faded. We are passengers on a ship with a destination, but the voyage is so long that the constellations as we know them will dissolve into new patterns long before we arrive. Our motion is a testament to patience, a reminder that the universe operates on a clockwork of unimaginable scale, where even 1,000,000 miles per hour is just a gentle, stately drift toward an inevitable, distant gathering. This cosmic push from nothing forces a profound shift in perspective. For centuries, our understanding of the universe was built on a simple, intuitive principle that matter is what matters. Stars, planets, galaxies, these were the engines of influence, the luminous actors on the cosmic stage. Their gravity was the hand that sculpted orbits and drove motion. Emptiness was just the backdrop, the passive, dark curtain between the points of light. The discovery of the dipole-repeller shatters that comfortable view. It reveals that voids are not merely passive, they are active participants in the grand design, possessing a kind of negative gravitational charge. Their influence is not exerted by what they are, but by what they are not. It is the absence of matter that creates the slope, the lack of stuff that generates the push. This inverts our intuition. We are not only being guided by the shining mountains of the cosmos, but also by the silent, expansive valleys. Our fate is written as much by emptiness as it is by fullness. This carries a deep, almost poetic weight. It suggests that in the universe, as in life, influence is not solely the domain of the massive and the bright. The quiet spaces, the gaps, the voids, they exert their own powerful pull on the narrative, shaping the flow of everything around them by their very absence. It is a humbling reminder that we are responsive to the entire structure of reality, to both its presence and its profound lack. What does it mean for our place in this scheme? We are not merely subjects of attractive forces drawn toward centers of light and mass. We are also refugees from emptiness, subtly propelled by the great nothings that punctuate the cosmos. Our journey is a dialogue between the something and the nothing, and both voices are essential to the story. The universe is too vast for just one great void. If our local motion is orchestrated by a partnership between a hidden mass and a hidden emptiness, could similar duets be playing out across the cosmos? The answer emerging from the data is a resounding yes. The dipole-repeller is not a cosmic anomaly, it is a prototype. It reveals a fundamental rule of the gravitational landscape, where every great attractor likely has a great repeller as its counterpart. Think of it like the cosmic version of high and low pressure systems in Earth's atmosphere. A storm, a low pressure system, draws air inward, but that inward flow is only possible because of the higher pressure in the surrounding regions, which pushes air toward the low. In the universe, clusters of galaxies are the low-pressure zones, the gravitational storms. The voids are the high-pressure zones, the expansive regions from which matter is steadily evacuated. This means the cosmic web is not a static sculpture. It is a dynamic, breathing entity. Galaxies do not simply sit on the web strands, they flow along them, driven by the pressure differences between the dense knots and the empty bubbles. So, while the dipole-repeller has a special significance for us because we are on its axis, it is almost certainly one of many such titanic repellers. Astronomers are now searching for these other colossal voids, mapping the outflows of galaxies to trace the silhouettes of the great nothings that push them. In the distant universe far beyond our local neighborhood, they suspect the existence of repellers even larger than our own, voids so immense they dictate the motion of entire superclusters. This paints a picture of a cosmos governed by a complex, balanced network of pushes and pulls. It is not a simple hierarchy where everything falls toward a single, ultimate center. Instead, it is a vast, interactive system, a gravitational symphony. In this symphony, attractors are the deep, resonant bass notes, creating wells that draw matter in. Repellers are the sustained, high notes, the expansive chords that create the space and the slope for motion to occur. Each galaxy is like a single instrument, its motion a melody composed by the combined influence of all the notes in its local cosmic chord. Our Milky Way's million-mile-per-hour journey is just one tune in an infinite composition, a specific harmony created by the particular arrangement of the Great Attractor and the dipole-repeller in our corner of the universe. This transforms our understanding of cosmic flow from a simple story of attraction into a rich, polyphonic narrative. We are not just being pulled, we are being carefully directed through an intricate landscape of presence and absence, where the silent, empty spaces hold as much compositional power as the brilliant, crowded ones. Mapping this silent partner in our journey demands tools of extraordinary vision. While we have inferred its existence from the motions of galaxies, the next step is to see the void itself with a clarity we have never achieved before. This is not about taking a photograph of darkness, but about illuminating the cosmic web with such precision that the silhouette of the dipole-repeller becomes sharp and undeniable. The future of this investigation lies with a new generation of space observatories, missions designed to survey the sky not in years, but in decades, charting billions of galaxies to trace the universe's underlying skeleton. Two missions in particular stand poised to revolutionize our view. The European Space Agency's Euclid telescope, launched in 2023, is now beginning its monumental 6-year survey. Its goal is nothing less than to create the most extensive three-dimensional map of the universe ever attempted, observing billions of galaxies out to distances of 10 billion light-years. Euclid carries two powerful instruments. One will measure the precise shapes of galaxies, looking for the subtle distortions caused by dark matter bending light, a phenomenon called weak gravitational lensing. The other will measure galaxy redshifts with immense accuracy. Together, these data will allow scientists to construct a map of both ordinary matter and dark matter with unprecedented fidelity. For the dipole-repeller, this means we will no longer have to infer its boundaries from a sparse sampling of galaxies. Euclid's map will show the void's edges in high definition, revealing how sharply the cosmic web transitions from the dense filaments around it into the profound emptiness within. We will see, in essence, the shape of the whole. Following Euclid, NASA and Nancy Grace Roman Space Telescope, scheduled to launch around 2027, will undertake an even wider survey. Roman's field of view is 100 times larger than that of the Hubble Space Telescope, allowing it to capture vast swaths of the sky in a single observation. Its core cosmology survey aims to pin down the effects of dark energy, but in doing so, it will also create an exquisitely detailed map of the large-scale structure of the universe. Roman will detect billions of faint galaxies and measure their distances, building a cosmic census so complete that the underdensity of a void like the dipole-repeller will stand out in stark statistical relief. Think of it like taking a population survey of a country. If you only sample a few cities, you might miss a vast, uninhabited desert. But if you meticulously count every single person in every town and village, the empty desert becomes glaringly obvious on the map. Roman will provide that kind of definitive census for our corner of the cosmos. With data from Euclid and Roman, astronomers will be able to weigh the void with new precision. By analyzing how the gravity of the surrounding matter deflects light from galaxies behind the void, they can measure the total mass that is missing from that region compared to the cosmic average. This will tell us not just where the emptiness is, but exactly how empty it truly is. Is it a perfect vacuum, or does it contain a faint, diffuse mist of dark matter and isolated stars? These missions will move us from knowing the void is there to understanding its intimate structure and its exact role in the gravitational equation that propels us. They will turn the dipole-repeller from a compelling shadow on our maps into a measured, quantified feature of the universe, a cornerstone in the architecture of our motion. This profound emptiness connects to the deepest mystery in physics: dark energy. For decades, we have known the universe is not just expanding, but that its expansion is accelerating. Something is pushing all of space apart with ever-increasing strength, and we call that something dark energy. It is the dominant force in the cosmos today, shaping the fate of everything on the largest scales. But what does this cosmic repulsion have to do with a void like the dipole-repeller? The connection is not just possible, it is likely fundamental. Think of the universe as a loaf of raisin bread baking in an oven. The raisins are galaxies, and the dough is the fabric of space. As the bread bakes, it expands, causing all the raisins to move apart from one another. This is the normal expansion of the universe. Dark energy is like yeast that becomes more and more active as the bread rises, causing the dough itself to stretch at a faster and faster rate. Now consider one raisin that is completely isolated, surrounded by a large pocket of empty dough. That pocket of dough, like a cosmic void, has less gravity holding it back. The surrounding dough, filled with other raisins and clusters, has more gravitational pull, which slightly resists the expansion. This means the empty pocket, the void, can expand slightly faster than the denser regions around it. This is not just a theory, it is a prediction of our best models. Voids are expected to be the primary theaters of dark energy's influence. With so little matter inside them to provide a counteracting gravitational pull, the repulsive force of dark energy can operate more freely, causing these empty bubbles to grow and stretch at a rate that outpaces the cosmic average. Over billions of years, this differential expansion could be subtly amplifying the repelling effect of voids like the dipole-repeller. The void is not just a static hole, it is a dynamic entity, potentially being inflated from within by the most mysterious force in existence. Its push on our galaxy might not be a constant, but a slowly growing influence as the emptiness behind us becomes ever more empty, ever more expansive. This transforms our understanding of the cosmic landscape from a fixed sculpture into an actively stretching canvas, where the blank spaces are growing faster than the painted ones, continually reshaping the slopes and gradients that guide our journey. This push from emptiness is often misunderstood. A name like the dipole-repeller sounds like something from science fiction, a cosmic engine emitting a beam of repulsive force. That is not what is happening. The void is not actively shoving us away. There is no mysterious energy field or exotic anti-gravity at work here. The physics, while profound, is rooted in the classical, well-tested understanding of gravity we have had for over a century. The repeller's influence is entirely passive. It is the gravitational equivalent of being in a room where one wall has been removed. You are not pushed by the empty space, you are pushed by the greater density of the crowd still at your back. All the surrounding matter in the universe, from the galaxies in our filament to the dark matter we cannot see, exerts a collective pull. Because one direction has a staggering deficit of that matter, the pull from all other directions is no longer balanced. We experience that imbalance as a net force away from the void. It is a push only by comparison, a one-sided tug in a universe that forgot to tug back from one particular quadrant of the sky. This clarification is crucial because it grounds a seemingly fantastical idea in the bedrock of established science. The dipole-repeller is not a challenge to Einstein's theory of gravity. It is a stunning validation of it on the largest scales imaginable. The equations predicted that such underdensities should have this exact effect, and the universe, in its silent way, has provided the demonstration. Another common misconception is that this void is a perfect, absolute vacuum. It is not. Calling it nothing is a useful shorthand, but the reality is more nuanced. The dipole-repeller is not a region of pure, empty spacetime. It is an underdensity, a place where the average number of galaxies per cubic million light-years is dramatically lower than the cosmic norm. Within that vast bubble, there are still a few isolated galaxies, adrift like lone ships on an endless, dark sea. There is still the faint whisper of the cosmic microwave background radiation, the afterglow of the Big Bang permeating every cubic inch. And there is almost certainly dark matter, the invisible scaffolding of the universe, though even that is believed to be far more thinly spread here than elsewhere. So it is not a true nothingness, it is a profound emptiness, a desert so vast that the occasional oasis only emphasizes the sheer scale of the barrenness around it. This matters because a perfect vacuum would have slightly different properties. The fact that it is merely an extreme underdensity, a place where the cosmic web has failed to form, is what allows us to model its gravitational effect with such precision. We are not dealing with an unknown physical phenomenon, but with a known one operating in an environment of extreme scarcity. Sensationalist claims sometimes leap from this discovery to wild speculation. You might hear suggestions that the dipole-repeller is a gateway or a tear in the fabric of space-time, or that it is evidence of a parallel universe exerting pressure on our own. These are compelling narratives for fiction, but they have no basis in the observational evidence. The data tells a simpler and in many ways more awe-inspiring story. It tells us that the universe has a structure, a topography of hills and valleys made of matter and dark matter. We are sliding down one of those slopes. The gateway is not a portal, it is a direction. The pressure from another universe is just the collective gravity of our own universe, unevenly distributed. The true wonder lies in accepting the reality as we have measured it, a reality where the arrangement of nothing can be as influential as the arrangement of something. This discovery does not require new physics, it requires a new perspective. We must learn to see the gaps in the cosmic canvas not as blank spots, but as active elements of the composition, their absence defining the flow and form of everything that is present. The push we feel is the signature of the grand design, a reminder that in the cosmos, influence is not always about what you add, but often about what you leave out. The human story behind this discovery is as compelling as the science itself. To truly grasp its significance, let us step into the shoes of the researchers. Imagine for a moment a conversation with the lead scientist, Yehuda Hoffman. We might ask him what was the eureka, a moment when the data first whispered the truth about the void. His answer would likely be humble. In science, breakthroughs are rarely a single flash of light. They are more like a slow sunrise where the shape of the landscape gradually becomes clear. He might describe staring at the supercomputer simulations, watching the predicted galaxy flows fail to match reality again and again, until they introduced that vast spherical underdensity. The moment the two lines on the graph, the simulated motion and the observed motion, finally converged into one, that was not a shout of triumph but a quiet sigh of understanding. The universe had been hiding an answer in plain sight, written in the language of absence. Our next question would probe the struggle. What was the biggest challenge in convincing the scientific community, and perhaps even yourselves, that a void could be so powerful? The challenge, he would explain, is always one of perspective. We are conditioned by centuries of astronomy to think in terms of luminous objects, convincing peers to take seriously the gravitational influence of a region defined by what it lacks requires a mental shift. The data from the Cosmic Flows project was the key, the hard numbers that showed a coherent flow of thousands of galaxies all moving away from that same patch of sky. The evidence was not in a single dramatic observation, but in the relentless statistical consensus of millions of data points. The biggest hurdle was overcoming the instinct to look for a brighter, more massive thing, and instead accepting that the dominant signal was coming from a darker, emptier place. Finally, we would ask the grand question: what does this discovery fundamentally change about how we see our place in the cosmos? His answer would bring it all home. For decades, he might say, we saw ourselves as passive subjects of gravity pulled toward mass. Now we understand we are active navigators of a textured landscape. The dipole repeller teaches us that the cosmos is a balanced system of tensions. It is not a hierarchy with a single center, but a web of relationships between dense clusters and empty voids. Our journey is not a fall into a pit, but a flow along a gradient created by the entire structure. This means our local motion is a direct reflection of the large-scale architecture of the universe. We are, in a very real sense, reading the contours of the cosmic web by feeling the slope beneath our feet. It democratizes influence, showing that the great nothings hold as much sway as the great somethings in charting the course of galaxies. That is a profound and beautiful shift, from a universe of simple attraction to a universe of complex, elegant dialogue between presence and absence. Visualizing this cosmic push and pull reveals a breathtaking landscape. To truly understand our place within it, let us embark on a journey, a flight through the local universe. Our trip begins right here at a single, swirling spiral of stars, the Milky Way. We pull back and our galaxy shrinks to a point of light, one among dozens in our local group. This entire cluster is already in motion, a flotilla of islands adrift on a dark sea. Now the camera pivots and we begin to travel in the direction of our motion. Immediately, the scale becomes overwhelming. We streak past the silhouettes of countless other galaxies, each a city of billions of stars. As we accelerate, a pattern emerges. These galaxies are not scattered randomly. They align into great, luminous rivers and tendrils, the filaments of the cosmic web. We are flowing along one of these rivers. The space around us glows with a faint, structured light, a three-dimensional map of matter. Now, look behind our path. The region we are leaving begins to darken. The glowing filaments thin out, the bright knots of galaxy clusters grow rare and then vanish entirely. We are approaching the edge of the dipole repeller. On our screens, this vast void is not shown as pure black, but as a profound, translucent blue sphere, an immense bubble of near-nothingness. The density map shifts from warm yellows and reds of high density to cool blues and purples of extreme underdensity. The glowing rivers of the cosmic web flow around this sphere like water around a giant bubble, refusing to enter. This is the source of the push, the great absence. Our flight path, traced by a brilliant white line, shows us skimming the void's outer boundary, being propelled forward by the greater density at our backs. We do not enter the void, we are pushed along its rim. Now we turn our gaze forward. Ahead, the cosmic web grows brighter, denser, more tangled. The filaments converge like tributaries flowing into a mighty river. The colors on the density map shift from blue to green to intense red. We are approaching the gravitational well of the Great Attractor. Though it remains hidden behind the dust of the Milky Way, our simulation reveals its influence. Flow lines representing the motion of thousands of galaxies curve and converge toward this one invisible point, a cosmic whirlpool drawing in the entire neighborhood. Our white path line bends, swept into this grand confluence. The final view is a panoramic shot from the side. We see the Milky Way's journey as a graceful arc across millions of light years. At one end of this arc, a giant blue sphere of emptiness, the dipole repeller. At the other end, a concentrated knot of crimson light, the Great Attractor. Between them, a river of galaxies with our own as a single spark, flowing steadily from the realm of nothing toward the heart of everything. This is not an artist's impression, it is a data-driven portrait of our reality. We are not still, we are in flight, forever navigating the invisible topography sculpted by the universe's most dominant features, the brilliant clusters and the silent, pushing voids. Such a perspective shift forces a startling question. What if our cosmic address were different? What if, instead of residing in a relatively dense filament, our Milky Way galaxy was born deep within the heart of the dipole repeller itself? Our entire experience of the universe would be transformed, beginning with the most fundamental human act, looking up at the night sky. From within that colossal void, the heavens would tell a story of profound loneliness. The first thing an astronomer would notice, even with a modest telescope, is the crushing darkness. In our reality, the Virgo cluster, a rich gathering of over 1,000 galaxies, is a prominent feature in our sky. From inside the void, it would be a faint, distant smudge if it were visible at all. Our nearest galactic neighbors, Andromeda and the Triangulum Galaxy, those hazy patches we can see with the naked eye, would simply not exist. The local group would be scattered, its members isolated by millions of light-years of empty space. A powerful observatory pointed in any direction would see mostly blackness, punctuated by the rare, faint glow of an isolated island universe drifting in the immense dark. The cosmic web, that grand architecture of filaments and clusters, would be an abstract theory, not an observable reality. We would see only the barest hints of structure, like a single thread glimpsed from the middle of an empty desert, with no sense of the vast tapestry it belongs to. The universe, from that vantage point, would appear not as a crowded metropolis of galaxies, but as a desolate expanse where stars are the only common light. This profound emptiness would have redirected the very history of science. The great debate of the early 20th century about whether spiral nebulae were part of our Milky Way or separate island universes might have lasted much longer or even tipped the other way. With so few external galaxies visible and no obvious nearby examples, the evidence for a universe filled with independent galaxies would have been far weaker. Edwin Hubble's revolutionary discovery of Cepheid variable stars in the Andromeda Nebula, which proved it was a separate galaxy, might never have happened because there would have been no comparable, nearby galaxy to study. The concept of an expanding universe gleaned from the redshift of many distant galaxies would have been much harder to establish with such a sparse sample. Our entire cosmological timeline would have been delayed by decades, perhaps even a century. We might still be debating the scale and nature of the cosmos, trapped in a lonely island universe with no clear map of the greater whole. Furthermore, without the clear gravitational flows from nearby attractors and repellers, the discovery of dark matter and the mapping of large-scale structure might still lie in the future. We would lack the local motion that provided the first clue that our gravitational models were incomplete. From the heart of the void, the universe would seem static, uneventful, and overwhelmingly empty. Our philosophical understanding of our place in the cosmos would be fundamentally different, shaped not by a sense of being part of a vast, interactive web, but by the haunting experience of being a solitary outpost in an endless, silent sea. This thought experiment reveals a humbling truth. Our scientific progress is not just a product of our ingenuity, but also of our location. We see the universe we do because we are positioned in a relatively rich neighborhood, a place where the clues to the grand design are plentiful. Had we been born in the great nothing, the mysteries of the cosmos would have remained hidden for far longer, shrouded by a darkness so complete it would have obscured not just light but understanding itself. This grand push from a cosmic void feels utterly remote, a force operating on scales so vast they defy human comprehension. But could its subtle influence ever reach down, not just to our galaxy, but into our own solar system or even to Earth? The answer reveals a fundamental truth about the hierarchy of forces in the universe. Within the confines of our solar system, the gravity of the Sun is the undisputed king. Its pull holds the planets in their precise clockwork orbits, a grip so powerful that the combined gravity of every other star in the Milky Way is nothing but a faint, negligible whisper in comparison. The Sun's gravity creates a steep, local well in spacetime, and we are all rolling around in the bottom of that well. The dipole-repeller, for all its grandeur, is like a distant mountain range causing a continent to tilt ever so slightly. That continental tilt is real and powerful for the continent, but it does not change the path of a single pebble rolling down a hill in a local valley. The pebble's path is dictated by the shape of the hill itself. So, while our entire galaxy is being pushed by the void, every star, planet, and speck of dust within it is overwhelmingly bound by the much stronger, much closer gravitational fields of their immediate surroundings. The Milky Way's core, the local spiral arm, our Sun, these are the hills that define our daily cosmic experience. The void's push is a background drift, a setting for the entire stage, but not a director of the actors upon it. This hierarchy extends upward. Consider our galaxy's own motion within the local group. The Milky Way and Andromeda are locked in a mutual dance, orbiting their common center of mass, destined to collide in billions of years. This intricate orbital waltz is governed almost entirely by the gravitational pull between these two giant spirals and their satellite galaxies. The push from the dipole-repeller does not alter this dance. It simply moves the entire dance floor through the wider universe. The void sets our group's trajectory, but not the internal motions within the group. It is the difference between being on a cruise ship sailing across an ocean and walking from your cabin to the dining hall. Your walk is governed by the ship's interior layout. The ocean's currents set the ship's course, but they do not determine where you turn left or right inside it. This principle of scale is universal. From the orbit of Earth around the Sun, to the Sun's path around the galactic center, to the Milky Way's flow within the local group, local gravity always wins. The influence of larger and larger structures only becomes dominant when you zoom out to the scale of galaxy clusters, filaments, and superclusters. It is at that ultimate scale, the scale of the cosmic web itself, that the push from the great voids finally rises from a faint background hum to a defining roar. The dipole-repeller's power is not in moving individual stars, but in moving the entire river of stars in which those stars are embedded. This layered understanding is crucial. It means we can study the mechanics of our solar system in perfect confidence, knowing its rules are local and secure. Simultaneously, we can lift our gaze to the horizon of the observable universe and understand that those same, secure local systems are collectively adrift on currents born from the largest structures and absences in existence. Our reality is nested, a gravitational tapestry where each scale has its own dominant weaver, from the Sun's tight knots to the void's expansive, pulling threads of nothingness. The story of our motion is no longer a simple tale of attraction. This discovery marks a quiet revolution in how we map the cosmos. For centuries, astronomy was the study of light, of finding and cataloging luminous objects whose gravity could pull. The very idea that a dominant force could be traced to a place of profound darkness required a fundamental shift in thinking. Our textbooks are being rewritten, not with new laws of physics, but with a new layer to an old map. The standard model of cosmology always predicted that voids should exist and have an effect, but they were often treated as passive byproducts, the empty spaces left over after the glittering cities of galaxy clusters formed. The dipole-repeller forces us to promote voids to principal characters in the narrative. They are not leftover scenery, they are active sculptors. This changes our models of large-scale structure formation from the ground up. When cosmologists run simulations of the universe's evolution, they must now pay as much attention to the growth and dynamics of these vast, empty regions as they do to the clusters. The push from a repeller is as integral to the cosmic flow as the pull from an attractor. This is a more complete, more balanced picture of the gravitational universe. It showcases the incredible power of modern data analysis. This was not a discovery made by a single telescope peering at a new object. It was a discovery made by connecting millions of data points across the sky, by tracking the subtle drifts of thousands of galaxies, and by asking the right question of the numbers. It is computational cosmology at its finest, using supercomputers to reverse engineer the universe from its present-day motions. We are no longer just observers, we are cosmic detectives, reconstructing events from forensic clues scattered across hundreds of millions of light years. The paradigm has shifted from seeking only what shines to also mapping what shadows. understanding that in the grand design of the cosmos, the empty spaces hold the pen as often as the points of light. Yet with this new map comes a fresh set of mysteries, each one more intriguing than the last. The dipole repeller is no longer a question mark, but its confirmation has sketched only its silhouette. We know it is there, but what is it really? First, its precise shape and internal structure remain elusive. Our maps show it as a vast spherical underdensity, but is it perfectly round or more like a cosmic amoeba with complex, undulating borders? More critically, what is its density profile? Does the emptiness increase sharply at its edge like the wall of a bubble, or does it fade gradually, a gentle slope into nothingness? Is the void completely uniform in its emptiness, or are there faint, wispy tendrils of dark matter weaving through its interior, the last remnants of a web that failed to form? These details are not trivial. They hold the key to understanding how such a colossal structure emerged from the nearly smooth soup of the early universe. The formation story is the second great puzzle. How did a region hundreds of millions of light years across end up with so little stuff? The leading theory points to the primordial seeds of the cosmos, tiny quantum fluctuations in the fabric of spacetime just moments after the Big Bang. These microscopic ripples were stretched to cosmic proportions by inflation, the universe's explosive initial growth spurt. Areas with slightly more density than average became the seeds for galaxy clusters and filaments. Areas with slightly less density became the seeds for voids. The dipole repeller would have started as one of these subtle, underdense patches. Over billions of years, gravity acted as a cosmic real estate agent. Matter was steadily evacuated from the underdense region, drawn toward the growing dense regions around it. The void emptied out, becoming more pronounced with time. But is that the full story? Could there have been a rare, colossal underdensity from the very beginning, a primordial bubble that set the stage for this great nothing? Simulations can recreate the general process, but matching the exact scale and emptiness of our local void is a challenge that tests our models of the universe's infancy. The third mystery concerns an even grander flow. Our local group's motion is part of a larger current, a river of galaxies hundreds of millions of light years wide. This current is directed toward the Great Attractor and away from the dipole repeller. But is this current itself part of something even vaster? Some cosmologists speculate about flows on scales of over 1 billion light years, movements so immense they might be influenced by structures beyond the edge of our current surveys. Could the dipole repeller and the Great Attractor themselves be drifting, caught in a gravitational tide set by superstructures we have not yet mapped? Are we, in our quest to understand our motion, merely charting the smaller eddies in a cosmic river whose true source lies in the deepest darkness of the observable universe? These are the frontiers. Every solid answer science provides does not end the conversation. It simply refines the questions, peeling back one layer of the cosmic onion to reveal another, more complex and fascinating layer beneath. The void pushed us toward a new understanding, and that understanding now pushes us toward new, deeper mysteries. Our journey began with a simple, staggering fact: our galaxy racing through the void at over 1 million miles per hour. For decades, the prime suspect was a hidden concentration of mass, the Great Attractor, pulling us toward the constellation Centaurus. But the math never added up. The pull was too weak, leaving a cosmic mystery in its wake. The full force behind our motion demanded a bigger explanation, one that would come not from seeking more light but from mapping the profound darkness. The breakthrough revealed a second, invisible hand, the dipole repeller, a void of staggering emptiness hundreds of millions of light years across. This is not an object, but an absence so vast it creates a gravitational slope, effectively pushing our entire galactic neighborhood away from it. We are caught in a grand, cosmic tug of war, pulled by a hidden mountain of matter ahead and pushed by a hidden ocean trench of nothingness behind. This elegant balance reveals the true nature of our universe, a dynamic, breathing entity called the cosmic web, where brilliant filaments of galaxies are shaped as much by the silent, expanding voids between them as by the glittering clusters. Our motion is not a simple fall into a pit, but a stately flow along the contours of this largest of all structures, a journey set in motion billions of years ago. This story transforms our place in the cosmos from passive subjects of gravity to active navigators of a textured, invisible landscape. It teaches us that influence in the universe is a dialogue between presence and absence, where what is not there can be as powerful as what is. So we turn the question to you: which cosmic mystery captures your imagination the most? Is it the nature of dark energy stretching the voids, the search for other colossal repellers, or the ultimate fate of our galaxy in this infinite web? Share your thoughts below, and if you want to join us for more deep dives into the wonders of space, be sure to subscribe.